Every flight needs a pilot, like me. But today I have a helpmate, an automatic landing system to bring me down safely, even in the thickest fog. This plane is the Trident, one of Britain's second-generation jet airliners. There's another, the VC-10, off across the Atlantic, probably. And the third, the 111. That's the short-haul specialist. The Trident comes somewhere between. You can see them now in airports all over the world in all kinds of airline colors, side by side with the first generation of British jets, still giving fine service. Take London Airport. There's the Comet, the world's very first pure jet airliner. The Britannia, a prop jet and the first turbine-powered plane to fly a regular passenger service across the Atlantic. The Viscount, the first prop jet ever to go into passenger service. It developed into the Vanguard, bigger, faster. Then come freighters like the Argosy. And the many, many planes built abroad, but with British engines. The French Caravelle, the Dutch Friendship, quite a few 707s, and DC-8s too. It's a good record. A record of an industry leader which serves the whole world. What does it take nowadays to build a plane like this? What kind of industry has to exist to do it? In many ways, the industry has a new look. Many of the great names of the past, de Havilland and Hawker, Vickers and English Electric, have come together to make bigger units, more efficient, more competitive. It's a big industry. Labor force about 200,000. Annual turnover 500 or 600 million pounds, with over a third going on research. But these are just facts and figures. Take a look inside. Britain's aerospace industry is one of the few really comprehensive ones in the whole world. It makes a complete range of aircraft, from the great long-distance VC-10s to sophisticated executive jets like the 125. A wide range of helicopters, made and exported. Missiles, rockets, and satellites too. And the means to power them. British engines power about half the turbine passenger planes of the Western world. Supporting these are literally hundreds of firms and thousands of people making components and equipment. These too finding their way into many planes other than British. Equipment becoming more intricate, more delicate. Factories becoming more clinical and antiseptic. While behind every aspect of production are the men who plan, design, and draw. The planes in service today, the shapes of the planes of tomorrow.
This plane is the 115. Pilots like me think it's a great plane, but it's one on its own because it was designed just as a research tool to see how the delta wing shape for the Concorde airliner handled at low speeds. The shapes of new aircraft get their first practical testing, though, in wind tunnels. This is one of over 100 variants of Concorde which have been tested, and this is one of the key test tunnels. All necessary to test a 6-foot model at twice the speed of sound. Past the sound barrier and on to Mach 2. Oil picks out the airflow over wings and fuselage. Smoke picks out the vortices. The model can even be flown. Crammed full of instruments, it's taken up to several thousand feet before being dropped. Its programmed flight path is recorded all the way for later study. And after models, actual research aircraft. The 221 for high-speed work on the delta shape, the SC-1 for vertical takeoff research. It was the world's first. In the future, how about a transport to take 200 people non-stop halfway around the world? Or an Airbus to take 150 passengers entirely within the contour of the wing. Or a plane which alters the shape of its wings in flight. Or wave riders, planes to travel at 4 times the speed of sound, the transport of the 1980s. Fantasies? More like fascinating possibilities which only further research and development can make practical, as this 115 has helped Concorde. You can't have a world-class industry without investment in research.
And after research, the production aircraft. Take the airframe alone. It must be light, yet strong. One way to get strength is to mill from the solid. In shaping it, you might mill away about 90% of the original block, but you'll keep its essential soundness. Another way is to use resins to bond the various parts together. They become the filling in a kind of great metallic sandwich, clamped permanently together in the jaws of one of the world's most powerful presses. The result is a bond as strong as the metal itself. Airframe and engines. Engine production makes, if anything, even heavier demands on technology. They are now tested in special chambers at twice the speed of sound and at altitude conditions to over 70,000 feet. Helped by facilities like these, today's British jet engines have been developed. The turbofans like the Spey and Conway, more efficient, more economical. Tested to stand great heat and pressure, and yet needing parts made with fine precision in very tough metal. So new techniques of production have had to be pioneered. Techniques like spark erosion to burn perforations for air-cooled vanes. Techniques like electrochemical forming to mold shapes of great intricacy. Techniques using an intense electron beam for working metals too hard to cut and weld with normal methods. These are the frontiers of technology. But even with everyday machine tools, the industry is out in front. And there's new material being developed too, non-metallic, weight-saving. It's on this firm basis of technology that the achievements of the engine side of the industry have been built. From the trusted prop jets, through current innovations like the Pegasus vertical takeoff engines, and on to developments of the future like ramjets. 4 times the speed of sound. These are the engines to drive the passenger planes of 20 years ahead, being tested now in Britain. Airframe, engines, and equipment. What's needed to service a modern airliner? Over the equator or the Arctic, and whatever the height, you need a pressure and temperature control system. On the flight deck, instrumentation has to be fuller than ever before, and yet incredibly sensitive and accurate. While to process flight data are aids like the black boxes, small computers which act as the aircraft's electronic memory. To keep all these systems working, often triplicated for extra safety, can take up to 50 miles of wiring. Even a familiar piece of equipment, like an undercarriage, can do the unexpected. Like squatting, to lower the fuselage nearer to the ground for ease of loading. And so, the many different skills come together to make the complete aircraft. And they're in evidence in every new plane the industry produces.
It's always the way. The glamour planes get the attention while the choppers do the work. Army assault transport for the Wessex. Reconnaissance work for the Wasp and Scout. Air-sea rescue for the Whirlwind. There's our man. Some people never learn. Soaked to the skin trying to row across the channel when he could have been riding on a cushion of air. Hovercraft. Large and small, hovercraft are already making scheduled passenger runs in many parts of the world. They're being used by the military too. on Britain's Isle of Wight is the world's only production line of hovercraft. This line is now being greatly extended as the giant SRN-4 enters production. A hovercraft to take over 250 passengers and over 30 cars. The future for this newest form of transport is certainly unlimited.
In a real emergency, a man's life would have been saved. Safety. No other industry goes to such lengths to test its product. How does an undercarriage stand up to repeated heavy landings? How do the linings stand up to sudden braking at takeoff speed? To find the answers, test. And test again. Aircraft, like cars, have to start when cold. This spey has been standing for 3 days at -40 degrees centigrade. But a first-time start is still expected. After all, if an aero engine fails, you just can't coast to the side of the road and phone a garage. Now accelerate. Infrared radiant heaters glare down on a cockpit canopy. Carbon dioxide at pressure is the coolant. The aim? To simulate the effect of high-altitude flying at supersonic speeds. The life of the pilot depends on the canopy's resistance. Everything is tested. Britain has over 100 engine test cells engaged in routine testing alone. Every piece of equipment, too, from the bolts on doors to the latest navigational aids. And when the individual pieces of equipment come together into aircraft systems, these too must be tested. The entire electrical layout, for example. Finally, the complete systems of the plane to be. Pilots can see exactly what happens to every movement of the controls and get experience of the aircraft long before it ever flies. Another element of safety is in air traffic control. With traffic getting heavier every year and the coming of supersonic passenger flights, control equipment has to perform outstandingly. Take one of the latest ideas, secondary radar. A plane isn't merely tracked, but interrogated too, quite automatically, about its height, for example. The more ground control can find out about the planes in its area, the safer still can flying become. For all kinds of planes, great and small. like the 206. Just the thing for the busy executive whose time costs money, and with flight deck equipment up to airline standards. Of course, if you're really one of the pillars of industry, it'll have to be the 125. With its 2 Viper jets, it's faster than most airliners and the last word in luxury. For a workhorse, there's the Skyvan, robust and roomy, and designed to take off from simple grass strips. Like the Islander, intended for feeder services from outlying areas, inexpensive to buy and to operate. Then come the medium-sized transports, established export successes like the 748 and the Herald. 9 out of every 10 Heralds built go for export. And besides all these, the military planes, like the Lightnings. The supersonic Lightning is an Air Force fighter. The Navy's new strike aircraft is the low-flying Buccaneer. Most unconventional of all are the Kestrels, with their special vectored thrust Pegasus engines. They formed in Britain a special 3-nation squadron, which was the world's first for vertical takeoff. The Belfast is the first strategic transport to be built in Britain, and one of its biggest planes ever. Alternative loads include 150 combat troops, or even 4 helicopters. To complete the roll call, bombers like the Victor. And trainers like the Gnat and Provost. Another side to defense, unmanned craft, missiles. Altogether, providing a complete and comprehensive defense system. Rockets aren't just for the military. Nowadays, they're an essential part of space research. Britain's biggest is Blue Streak, test-fired at Woomera in Australia. It's now the first stage of Europa 1, Europe's major launcher scheme. And after rockets, the satellites they will launch, like the UK-3. Or this one, for the European Space Research Organization. Cooperation is in the air. For many years, of course, the industry has exported all over the world, and men have come to Britain to be trained. But current projects go far beyond this. A 4-nation consortium is building Tyne engines for the French Atlantic and Franco-German C-160 transports. British lift jet engines have been specially developed for German and French vertical takeoff aircraft. In one of the world's few vertical takeoff tunnels, research has gone ahead on several international projects. Even in production, cooperation is becoming the norm. And so, in Ireland, an English tape deck guides the milling of a part for a new Dutch plane. Plans are ambitious. A German-Dutch-British replacement for the aging DC-3. A new business and feeder jet to be marketed with American help. And biggest of all, the Anglo-French Concorde, the world's first supersonic airliner, and an aviation breakthrough as basic as the jet engine. Concorde is in production, of course. In Britain alone, it's meant a tremendous investment in new test centers, for structures, for the huge and powerful Olympus engines, French and English work side by side as Concorde takes shape. Cooperation in action. I wonder what other planes I'll see in the years ahead, and even fly. I've a good few years of front-rank flying left yet. Paris in 40 minutes this year, New York in 2 or 3 hours in a few years' time. What after that? One thing I'm sure of. There'll be a British industry involved, designing, building, pioneering, as they've done since the first years of powered flight, as they're doing now all over the world.